Okay, Samuel, let's start.
Okay, start already.
Now.
Tony, you can start because I have to go to airport to finish my preparation. How to see I don't want to see myself.
I also know there. But now I'm out of it.
To ai bari gaya maka password din ai a kunne yake. Password din shine 86. Simple. Ta ci je gaba? Har da sun sa mata rana sun ɗaure ta. Oh, pointer not working. Yeah, I think connect, right? Okay. Why battery? That is battery.
This one connected?
Yeah, it's not connecting.
No.
Oh, new one.
Yeah, no.
Wow. You buy from Japan?
Yo, no, in Thailand.
Yes. How to use?
Good afternoon, everyone. Today, as usual, we are going to have postdoc seminar presentation from 3 candidates. The first presenter is Dr. Jamila Abubakar, who will start now on the topic iterative method for split equilibrium problem and minimization problem via conjugate gradient method. Thank you very much for joining this program. Dr. Jamil, the floor is yours.
Okay, thank you very much, Mr. Chairman. Like the chairman rightly said, today we are going to continue our postdoctoral seminar series. And the topic of today, I will be discussing on the iterative method for split equilibrium problem and minimization problem via conjugate gradient method. Okay, so this is the overview of my talk today. I will introduce the whole idea. Then I give some preliminaries. Then I show the main result with some numerical examples. So let's now get acquainted with the setting. So suppose we have 2 Hilbert spaces, H1 and H2, and we have some convex subsets, closed and convex subsets C and Q. Given by functions also F1 and F2, we can see this is from C to R. So the split equilibrium problem, which was introduced by Mudapi and further studied by Kazimi in these papers, you can see the paper here, 2011, which was published in our Journal Optimization Theory and Application. And also the paper of Kazimi is Population Fixed Point Problem, Journal of Egyptian Mathematical Society. So the problem is given as that. You can see, if you look at equation 1 here, we are seeking to find a point U here in C such that this is satisfied. And also at the same time, the image of that point is also solving another equilibrium problem. If you look at it, these are two equilibrium problems. That's why it's called split. One is in C and the other one is in Q. Which were bounded, which were related by this linear transformation from H1 to H2. So, and also from the title, you can see we are interested in two problems, the split equilibrium problem and the minimization problem. That is a problem that we want to, this is a constraint minimization problem where we want to find a point in C such that it's a minimum of this function. So this problem has been studied severally in the literature and has many applications, for instance, in engineering, image processing, game theory, and economics. There are so many applications of this, especially when we talk about the equilibrium problem. It's a unified problem that you can derive the variational problem from it, inclusion problem, optimization problem, a lot of problems from it. So, and this, there are different iterative methods that has been studied over the year for this kind of common problems. And this iterative method, mostly they has to do with the fixed point iterative theory. They are derived from the idea of fixed point iterations. So this fixed point iteration that we already know, the basic of them that we can see here, we can have the man iteration, Halpern iteration, viscosity, and so on. These are iterations that were modified in order to solve this kind of problem. So let's now recall ourselves now for the minimization problem. Recall that in the fixed point iteration method, that a point x star here in C solves the minimization problem that I've shown earlier in equation 3, if and only if it is a fixed point of this operator, right? So where this is a gradient of the function that we are trying to minimize. So and consequently, due to this fixed point characterization, we can have an iterative method here using this operator. If you look at it, this is a kind of a Picard iteration where we can have, and this iteration has been shown to converge strongly to the minimum solution of this point. But the only thing here is there are some strong assumptions that needs to be considered in order to get the convergence here. For instance, now the operator here, the gradient of this operator involved needs to be inversely strongly monotone or strongly monotone for us to be able to establish the convergence, which is a little bit strong assumption if you look at it. So in order to, yeah, this is what I was trying to explain right now. So in order to have another alternative of proving, getting a convergence of this kind of method, Zhu, in this paper, average mappings and gradient projection, which was published in Journal of Optimization and Theory and Application, try to bring using averaging mapping as an alternative to using the previous characterization, because that one involves a strongly or inverse strongly monotone operator. So he get this convergence by using average mapping operator. So, okay, this is one of the aspects I want to talk about, because the idea here, we are trying to blend the averaging technique and also the conjugate gradient technique. Why the conjugate gradient, if somebody should ask? Ideally, the conjugate gradient was introduced in order to accelerate the convergence property of the steepest descent method, right? If you look at the direction here, without the additional time here, is the steepest direction. So this is the conjugate that they add this in order to have a faster convergence. So we want to take advantage of that acceleration process of conjugate gradient method, and also the averaging techniques because this was introduced for optimization problems. So now we want to we don't want to use the gradient of this function. We want to use it as some average mapping here. So let me recall some literature here. This paper used somehow not a similar idea, but he used the idea of conjugate here. This is a common solution of split variational inclusion problem with minimization problem. If you look at the second iteration, the second step here now, this is a conjugate step for the minimization problem, and this is for the inclusion problem. He used the idea in order to have an accelerated version of the algorithm. But here they did not use the average operator technique here. So, and these are the parameters where the lambda here belong to this, and this is a sequence of contractive mapping. So this is a kind of a viscosity type algorithm that they've used. And the operators, like I say, are maximally monotone operators. You can see these are set valued operators from H1 to this and this one also respectively. So like I already explained. So now what we want to do here now, what is interesting here now, we want to modify the conjugate direction here. Instead of using my gradient of the operator now, we want to use an average mapping approach. We want to move it and put some average mapping here. And later, before I show the main result, I will show you why we can be able to replace this with this. So before I go into the main result, I will show some preliminaries. This is the assumption that we take on the underlying operators, that the bifunction here needs to be greater than or equal to 0. You can see for all U1. And also this is like a kind of a monotonicity assumption on the F1 here, the bifunction. And also this, we say that F1 is upper hemicontinuous. And also if we have a fixed point here, a fixed point in C, this function is convex and lower semi-continuous. This assumption, we need them in order to show the convergence. And also this lemma, this is a kind of, to define a kind of a proximity operator now for the bifunctions here. And this has been already established that this operator here is single valued mapping. And also for every U1 and U2 here, you can see here is saying that it's firmly non-expansive. So, and we can, so this is like a kind of extension of projection, because it has properties like a projection, you can see. And also the fixed set of fixed point of this operator is equivalent to the set of the solution of the equilibrium problem that I've shown here in equation 1 and 2. And the solution set here of the equilibrium is compact and convex. So all this has been established, and we need this identity for the convergence, this inequality to show our convergence in the convergence analysis. Also, you can, if you are interested in this lemma, you can check the reference here. And also, this is a kind of a zoo lemma here where we used it in order to show the strong convergence. And I am sure we are all familiar with this one. So why the average mapping here? Let me recall also that we said a mapping is an average if it can be written as an average of an identity map and a non-expansive map. So you can see here this is a non-expansive map. For not to say for abuse of notation, you can change this R to be maybe some operator T or something where it is non-expansive. And this AN happens to come from the interval 0, 1, and I here is denoting the identity mapping. So average mapping are well known to be non-expansive, and they are also firmly non-expansive mappings are also average. Yeah. So that operator that we define can be considered as average. And like I told you, okay, this is the main results here that we want to talk about. This is the setting now. Suppose, like I defined, we have this bifunctions, and also assumption that we've shown here has been satisfied. And also additionally to that assumption, you know, in the other one, we assume that the F1 to be lower semi-continuous, right? And in this case now, F2, we want it to be upper semi-continuous in the first argument. And this is a contractive mapping. And this is the bounded linear operator where this is the contractive parameter here. And this is the agent of our bounded linear operator, and we have the sequences, this satisfying these assumptions. These are normally assumptions that we always use to come across them. Okay. For instance, this rho by n, if we take 1 over n plus 1, this assumption can be satisfied easily. Okay. And also further, for the minimization function here, we assume that we have h as a real valued function where the gradient here is L Lipschitzian, you can see. And it has been shown that this mapping is an average. If you take, remember, we said that due to the characterization, fixed point characterization, we can have an iteration like this. So that's why we can take this one as an average operator, because it has been shown, for instance, in the paper of the zoo has shown that this is a 2 plus lambda L over 4 average. So that means we are saying that we can represent the whole of this as an average mapping. Yeah, instead of using this, so you see we are for some non-expansive mapping Rn here. Okay. So now for the sake of our analysis, let's suppose the solution set of the common problem to be this gamma, and also this to be U for the represent the solution set of the minimization problem, and omega to represent the solution set of the split equilibrium problem. Remember, we want to find the common problem, so we are interested in the intersection. So this is now let me introduce the proposed algorithm. For the algorithm, the initialization looks like this. We choose a sequence in this that satisfy those assumptions that I've shown. And also we take a sequence here in this such that this is a positive number, and also the same thing with this row, and such that this row is a positive number, and also satisfy the assumption C3, this assumption. Yeah. So now for the iterative step now here, we want to calculate, if given we have U, we generate UN, we want to compute Vn as given by this. Remember, this is the proximity operator that we've introduced. And now the delta N here now is given by this. This is a kind of a self-adaptive step size, which in the literature, remember I mentioned some work there, all the work I passed through, most of the other step sizes there, they are fixed step size, which they depend on some fracture, maybe depend on the Lipschitz constant on something. But here we define it in such a way that it will be self-adaptively updated from the algorithm, and it's given by this. And Vn are coming from this interval, and this eta n from this. So if Vn and Un are the same, then we stop. That means we are at the solution of the split equilibrium problem. And otherwise, we move to the next step where we compute. If you look at it, for those that are familiar with conjugate gradient, this is a kind of a conjugate gradient step, right? But the Vn here, remember how we compute it in the split feasibility problem. And this is the direction now. To update the conjugate direction, you can see now, instead of now the gradient of that function we are trying to minimize, we are using the average mapping technique here. So we don't need to have that assumption that the gradient needs to be strongly inverse the whole of it. So that is one of the interesting part about the algorithm. And also this is then we have the viscosity type combination at the end of the day. So if then we set n plus 1 and go back and repeat like this, this is the scheme. So this is the lemma, that our first lemma that we need in order to show the convergence here. We suppose UN be sequence generated by the proposed algorithm, and let the sequence here eta n be in 0 or 1 would satisfy this. Like I told you, this is not a very difficult assumption, because 1 over n can satisfy this. And also then we need this inequality, this relation, this forgive me, this should be less than or equals to. Okay. And this is the main theorem statement here. Suppose we have these two Hilbert spaces, H1 and H2, and the closed and convex subsets C and Q of this H1 and H2, and we have this by functions F1 and F2, we can satisfy this assumption. And F2 additionally, I said it's supposed to be is upper semi-continuous in the first argument. And this is a contractive mapping with a constant kappa here between 0 and 1. And we have a bounded linear transformation joining the spaces H1 and H2 with an adjoint A star. Then we have this sequence is also satisfying assumption C1 and condition C1 and C2. Then for any starting point we pick in C, then the sequence generated by the proposed method algorithm now converges strongly to the solution point in that. Where this is a minimum norm solution, you can see we can write it as a projection onto the point onto the solution set. And this point also happens to solve unique variational inequality of this form. Okay. So I did not bring the proof details of the, because this work is still work that is under review, is still ongoing. I did not bring some of the technical proof in the work, but I will show you the numerical examples to see the potential applicability of the method and how the method, like with the conjugate techniques, makes it fast and that. And we perform all our computation in MATLAB 219 running days and with this specification. And this is the first example. We take a very simple example here in R, where we define C to be this interval, Q to be this, and F1 defined by this, the bifunction, and the bifunction, second bifunction defined by this. So this can be easily computed using, you can easily get this operator from the definition where you define this operator to be that this, and the proximity operator also with respect to the first bifunction can be calculated like this. And now, for the sake of the numerical illustration function. So for the parameters, we choose the parameter, the contraction function to be u over 6 and the bounded linear operator to be -2 over u. And we set the sequences to be this. So, and for the stopping criteria here, we set it to be, so after when it is less than, or when the difference between the iterate is the norm difference between the iterate is less than or equals to 10 raised to the power of -6. So, and you can see the convergence behavior of the algorithm. This is for the tolerance here, and the convergence behavior of the algorithm very well here. This is the error against the iteration of the sequence. On the next example, we take R3 here. This is also a simple example in R3 where we define the C and Q, we take them to be this, and we take R to be this. So we can see that with this definition now, if we define the bifunctions here to be this and this, we can get those operators TF1 given by this and TF2 given by this. And for the illustration here, we set the control parameters here to be these sequences. These are simple sequences that satisfy all those conditions in our main result. So, and this, we give a table of this, forgive me also, this is a typo, this should be just the tolerance. We want to say this, we stop after, less than when the previous iterates are less than or equals to, 10 raised to the power -4 here, we vary it to see the behavior. And also we vary the initial starting point to see. So you can see the number of iteration when you take different types of the sequences. We see that here we have good result here when we take the sequences, the beta n to be defined by this and theta n to be defined like this. This is where we have the best result here we can see. But we can see that the algorithm is consistent in terms of the convergence and the results are okay. So this is to illustrate what I've just shown you here with one of the, we vary the beta n and the gamma n because we realize they are the sensitive control parameters in the algorithm here. So we try to vary them and see the behavior. You can see that the second and the third, they are almost the same. While when the first one is the one that converges slowly. Yeah. And so now we also give a comparative okay. I think Okay. For the last result, I gave a comparative result with an algorithm that was proposed by Kazimi in the paper I show you there. This is a comparative result between our algorithm. This is the proposed algorithm here that I've shown you as the Kazimi algorithm. In their algorithm also is an algorithm for solving split equilibrium problem, common solution with minimization problem. But in their own case, they did not use the averaging technique here and the conjugate gradient to get the accelerator. So you can see obviously here, this shows that our algorithm is way faster than their algorithm is here. Okay, thank you for your attention. And these are some of the references here that you can see, like the algorithm that we compare with. Yeah. Yeah, this is the algorithm. It's in this paper, the one we compare with, because this is for solving common solution operational and fixed point. So by the time you take the operator involved here to be the gradient of some function, then you are good. Okay. Okay, any question or suggestion, discussion? Yeah. No, we moved with a little bit back because of some technical issues. Yeah. Yeah, just 30 minutes, a little bit, and because it's online and most of the people are around, so that's why. And we have a lot of big class today. I mean, the lab, everybody is around. Okay. Well, the first advice I would like to give, I think, is the literature. One needs to go and find, because before we go into split equilibrium, there is the equilibrium itself. So split is an extension of that problem where you solve the same equilibrium problem in this side and another side. So thorough knowledge of the literature is required. Yes, and if that person happens to have a little bit experience in iterative methods that are related to the fixed point theory, I think it's not going to be that much difficult for him to, yeah. I think it's in terms of application, there are some real applications that can be designed and so they can be modeled in such a way that you are solving this problem in this, and at the same time, there is another problem, they are related. Even though this is not like directly a bi-level problem, but you can look at it as you have a problem trying to solve in this space where at the same time you are solving another problem in this. Yeah.
Thank you. With regard to the question, as he said,
yeah.
What
yes.
Which
yeah.
But I can see gradient
one interesting thing about this work is it's a kind of a work that we try to blend a lot of ideas here. We blend the averaging technique inside the conjugate method, that is one. And then we also blend the fixed point iterations inside. So I'm just trying to give it in a nutshell that I said the literature review. So that means when I made my literature review, even the equilibrium problem, you can't just start from equilibrium problem. Like I said, these iterative methods, they are all based on, fixed point iteration. If you look at it, I made mention of man iteration, because so you have to get familiar with those. There are a lot of things that need to be studied.
Yeah, I understand what I mean. For example, like the game,
yes.
But I think the best thing is to invite some of those experimentation and have no chance. Just maybe 5 steps of what going to be mindset.
Yes, that's the basic idea of that flow chart I'm giving you. Is that's why I just said it in a kind of a complex form that the literature review. What I mean by literature review, okay, if you want me to break it down, let's say you start from fixed point iterations, you understand? Because everything was built or based on that fixed point iterations. And the conjugate gradient technique you can of this optimization, which is very big, which obviously is a modification of another method, which is we mentioned the stupid design methods. So sorry to say, but as a layman, I don't know how to say where I should start because a lot of concept has been put in place here. Yes.
Thank you.
Yeah.
Can I see your argument?
Okay.
My question is from page 28,
Forgot.
and probably from there we go to.
Yeah.
So, as they have mentioned that he and the kind of like the parameter we could be sensitive.
Yes.
So just by changing the tolerance, and the iteration is really consistent with different.
Yes.
It's serious.
Yeah, because the tolerance is telling you how accurate it is. You get close to the solution. Like in terms of this, and also remember, it depends on what you define as your tolerance. Here we are taking the norm difference of the previous iterates. Another person can define it differently, but both on this algorithm, I think this is the best metric for us to measure how close it is to the solutions. Yes. Yes. Yes, yes. It's in terms of the accuracy.
So, if I talk about tolerance, what is the motivation behind the norm?
I think the motivation is, if you get close to the solution, the iterate now they will be sharing it, there will be zero. That's the motivation.
So you're thinking about, for example,
Yeah, that's why we are taking this metric. And no. Yeah. And also you should note that not every algorithm that this kind of method will work for it. It depends on the structure of the algorithm also. But in this case, this will work fine. And I would like to add also in terms of this beta parameter, because I see it created a lot of conversation. You can see why it will be, I thought you would have asked me that why didn't we just take like a fixed parameter for like the eta, is also a sensitive parameter in this. And the beta, you understand, we can take a fix to save this kind of problem. But due to in terms of eta, we are trying to have a self-adaptive, so we have to pay for some price. for this. That's the price that now we are paying.
The only challenge here is the fact that I'm not just randomly like any system to give them. That's the only problem we have.
Yes, yes.
So I think that you have the direction again.
Oh. Oh, okay.
Oh. So this beta is what we take as an arbitrary sequence.
Yes, and that's what I'm saying. It will have, I thought he will ask me that, why don't we just take a fixed number? It will save a lot of this problem and we will probably get a more faster.
And if you try to say that, then why is the conjugate number?
No, for our analysis, the beta n can be shown. It can be shown from, yeah, you are right. It's even 0 to half infinity, half. Yeah. So we have to, yeah, this is a typo, please forgive me. Yes.
Okay.
And
One more thing. Yes, from our analysis. Because in the comparison, we have to restrict the interval up to 1, and I say the work is in progress. I will have shown the comparison.
Okay. Something. Am I
The problem with classical beta here, one interesting thing I think and you can say something about is, you know, like the FR.
Please, you have 2 minutes to round up.
That the limit goes to 0. But here, we need the limit that goes to 0.
In that case,
So some of the beta parameter might not satisfy our assumption here.
in that case, then why don't you put like cases? Okay, use FR when certain things happen. If it doesn't happen, then you can use another.
But the problem with FR, it might not necessarily be a good choice for this algorithm because these are extension of optimization problem. And those ones were designed based on optimization problem. You understand?
Yeah.
So that's why we don't want to restrict to say FR, even though you, for illustration purposes, you can. But what I'm saying is, I gave you a simple example. The FR doesn't, I think, need the limit to be 0, right? But in this case, the limit can be 0. So it will not satisfy. Yeah.
Please, one question from on-site, and then we move to online. And you have only 5 minutes for, even if there is any question from the online.
Okay, Dr. Nasru, I think.
There is no beta key there. So
There is beta K here. You can call it beta K if you But I thought the conjugate gradient concept come from extending the steepest descent direction, right? And adding a time. Yes, and this is what we add here.
So why can't you choose the non-beta place of
That is what we are just. That's exactly what I'm explaining now. The reason why I cannot use the non-betas, for instance, the FR will not even work here because the limit of the beta doesn't necessarily need to be 0. The FR, but here it can be. We need it to be 0 by our assumption, so it cannot work. So this is like that's why I say the best way to call this is a conjugate like this. And that's what we call it.
Okay. Any question from online, please? On site? No. Any question from online? Okay, I think no question. Okay, Dr. Aliyu, please. Only one question.
Okay, no. If you want to use the conjugate, I mean, you want to use the non-classical.
Yes.
Why would you check if they are numerically stable? If you provide the way of thinking of how to do the comparison.
No,
Try numerically.
I did not honestly, but I have an idea of what is going to be. There is an Iduka walk that was there where he extend a conjugate like direction in terms of variational inequality.
Yes.
He made the comparison with the prominent beta parameters like the FR, whatever, you understand. But at the end of the day, he conclude that some can be good, but like PRP, he conclude is good for that, and FR cannot even satisfy his assumption. Yes. So I did not, it would be a good idea also to look at that one. Yeah. Yes, yes. Thank you very much.
Okay, thank you very much for this wonderful talk. I think we move to the next speaker.
Yeah. Only today, because I say conjugate. Before you this is next, go back. This is what next year. This is point. This is next year. Try. Yeah.
Now you can stand there.
Thank you very much. Now it's time for the second presenter, who is Dr. Bush, and he will be discussing on an outer quadratic approximation method for solving split feasibility problem. Yeah, you can start now. Thank you.
Okay, thank you, Chairman. Good afternoon, everyone. My name is Bush Haile Kaddada. Today, I will present one of my results titled "An Outer Quadratic Approximation for Solving Split Feasibility Problems." So these are the outlines of this presentation. So in the introduction part, I would like to start from what are inverse problems. As we know all, most of our works we did and we are doing are directly related to inverse problems. So inverse problems arise from the need to gain information about a known object of interest from the indirect measurements. So inverse problems have several applications in various fields of studies. And the common feature for inverse problems is the need to understand indirect measurements and to overcome extreme sensitivity to noise and modeling inaccuracies. And I think we are familiar with the well-known problem, which is called convex feasibility problem, which is the most applicable in modeling of many inverse problems. So this convex feasibility problem is defined as given in one. Let H be a real Hilbert space and C1 up to CT are non-empty closed and convex subsets of H. Then the convex feasibility problem is to find a point X star in the intersection of CIs, where I runs 1 up to T. And the intersection be assumed to non-empty. So this problem was initially arrayed in the constraint optimization to guess the feasible point of the problem, but later it was proved that this problem have great utility and applicability in many areas of spreading from modern mathematical and physical science to economics and medical practices. This convex physiology problem has been widely researched in the last decades, and many generalities of this problem have been studied. For example, among these generalities of the convex physiology problems, the most celebrated and applicable is the so-called split inverse problem, which is introduced in the first reference. And this split inverse problem is defined as this slide. Let X and Y be two vector spaces, and T from X to Y be a boundary and linear operator, and IP1 and IP2 be two inverse problems formulated in X and Y. Then the split inverse problem, which was introduced by Sensor et al., is formulated to find a point X star in X in the first space, such that which solves that the first problem, such that its image under the boundary line operator T, which belongs to the second space, solves also the second problem. So we can see here, by choosing different spaces, or by choosing different X and Y, including the case where X and Y are equal, we can have different types of inverse problems. Just this split inverse problem is just a model, but when we fix the IP1 and the IP2, we can have different types of the inverse problems. Like if IP1 is the equilibrium problem, and IP2 is equilibrium problem, so we will have that split equilibrium problem. If IP1 is the split physiology problem, and IP2 is a split physiology problem, so we will have that split physiology problem. So this is a general model that can be converted to particular or specific split inverse problems. So the first instance of this is split inverse problem is the so-called split physiology problem, which was introduced by Sensor et al. As well, Sensor and Elifin in 1994, and it is defined here. Let H1 and H2 be two real Hilbert spaces, and T from H1 to H2 be a boundary line operator. Then the split physiology problem is finding a point X star in H1 in the first space, which is in C, such that its image is in Q, where C and Q are the non-empty closed convex subsets of H1 and the H2 respectively. So we can denote the solution set of this split physiology problem by D, which is the intersection of C and the pre-image of Q. Actually, this D is non-empty closed convex subset, because C is non-empty closed convex subset, and Q as well. And the pre-image of a non-empty closed convex subset under a linear transformation is also convex. So this one is convex, and it is assumed to be non-empty. You can see here, sorry, this A is T. So we have this H1 and the H2, and this is C, this is Q. Then this one is the pre-image of Q under the linear and bound operator. So we are going to find X in the intersection of C and pre-image of Q. So this split physiology problem reformulation are employed successfully for many real-world problems, such as the IMRT, medical image reconstruction, the gear regulatory and network inferences, and so on. As I said, this problem was introduced by Sensor and Elifin. So by the time they introduced this problem, they proposed an algorithm which solves this split physiology problem. But the algorithm involves to compute the inverse of T at each iteration, assuming that the inverse of T exists. So in this case, computing of inverse of a matrix or an operator is difficult or costly. So this algorithm became not popular or not that much famous. So later, the most applicable and celebrated method introduced to solve the split utility problem is the so-called CQ algorithm, which was introduced by Sensor in 2002, and it is given here. For any initial point x0 in H1, the sequence xn generated by this 5, where PC and the PQ are the metric projections on C and the Q, respectively, of H1 and H2, where T star is the adjoint of T, and this tau n is tau n belongs to this interval, and this is the spectral radius of the matrix T star and T. So as we can see here, what we mean by metric projection is defined here. It is just the distance between a point X and its projection on C. Its projection on C is the minimum of the distances between X and each point Y belongs to C. So this operator PC from HC is called the metric projection of H on C. So from this method, from the CQ method, we can see we have two major drawbacks. The first one is the need to compute the projections onto the given set C and the Q. Most of the time, if the sets C and the Q are not simple, for example, like the union or the intersection, something like that, there is no a unique formula to compute the projection on the sets. So usually the metric projection onto the given or the involved set is somewhat difficult or costly. So this is one of the drawbacks of this method. And the second one is the requirement to compute the operator norm. That is this one. The step size depends on the operator norm. So in the way to solve the first drawback, an author Young, this researcher assumed the involved set C and DQ to be a level set of some convex functions. So he defined in this form where this C and the Q are convex and subdifferential functions on H1 and H2 respectively, and their subdifferentials are bounded on bounded sets. And then after this, they defined this these two sets. So for xn in H1 and the n in the subdifferential of the first function C, and the n is in the subdifferential of the second function Q. So they define this function, which is Cn and the Qn, where Cn is H1 if the subdifferential is 0. Otherwise, it is given in this form. And also Qn is H2 itself if the subdifferential is 0, and otherwise it is given in this form. So it is easy to see that these two sets are the supersets of the involved sets C and the Q for all n greater than or equals to 1. So consequently, they define this quadratic function, which is given here, and this function is convex and differentiable, and this gradient is given in the here. So after this Young's relapse CQ iterated method is given in this form. They introduced this method. So we can see here this projection is completed on the support status, on the half spaces, not on the involved status. So we know that the projection onto half spaces has their own unique formulas or closed forms. So it will be very easy to compute this projection onto the half spaces. But still, we can see that this tau n is given in the CQ method, so it still belongs to the interval between 0 and 2 over the spectral radius of T star T. So to solve the second drawback, Lopez in 2012 introduced a new form of step size time n, which is defined in this form. So this step size, we can see that it is self-adaptive. It can be evaluated self-adaptively by using 11, where this rho n is between belongs to this interval 0 and 4, and why this cannot move. If cannot move, please. Can you check, please?
Yeah.
On the screen.
Yes. What up? Move. Okay. Okay, so the iterative method introduced by Young with this step size given introduced by Lopez, we have a weakly convergent algorithm which solves the split feasibility problem. So as we know, in the real world, we know that there are infinitely many nonlinear problems that we have to be solved using different techniques. So in this case, the strong convergence is more desirable than the weak convergence. So many researchers propose the CQ extensionists that converges strongly to a solution of the split feasibility problem. So, for example, you can see that in 2012, Lopez et al. Introduced the so-called Halpern CQ method, which is given in this form, where this sequence alpha belongs to this interval and satisfies this condition, and then any sequence which is generated by this method converges strongly to the projection of this point, where this is the anchor, which belongs to the first space, and this is the initial point. So through time, a lot of methods introduced by different researchers. For example, we can see a different method which was introduced by Yu et al. In 2018 by using the projections onto another set, so-called closed balls instead of the involved sets C and the Q. So they considered that the sets given in 6, that's the level sets, with the functions C and the Q as lambda and omega strongly convex and subdifferential on H1 and H2 respectively, such that these two conditions satisfies. So Yu et al. Proposed an outer quadratic approximation. Actually, this the name quadratic comes from these pointers, from these quadratic terms. So they introduced that outer quadratic approximation method, or the ball relaxed CQ method, for solving the split feasibility problem, which is given by this one. Therefore, this is defined here. This is actually the step size. This is the step size, and this is the subdifferential. I mean the differential of the gradient of the convex function, but the projections are computed onto another sets we are given here C star and Q star, which are actually closed balls. So the projection onto closed balls has also a closed form or unique formula. So they proved a weakly convergence result under some suitable conditions. So through time, infinitely many generalization of this split physics problem have been studied. For example, we can see here one of the generalities of the split physics problem, which is multiple sets split physics problem. And it is defined in 16. Let H1 and H2 be two real Hilbert spaces, and T from H1 to H2 be boundary linear operator, and T star is adjoint. Then the multiple set physics problem consists of finding a point X star in the first Hilbert space with the property that X star is in the intersections of CI's I run 1 up to T, and such that its image under the boundary linear operator is also in the intersection of some finite family of non-empty closed convex sets in the second space in H2, where C1 up to CT and Q1 up to Q are non-empty closed convex subsets of H1 and H2 respectively, and T and D are given in integers. And we can donate the solution set of this multiple set split physics problem by this pi, and it's assumed to be non-empty. So a second generalization problem of this split feasibility is the generalized split feasibility problem, which is given in 17. Let Hj, J runs 1 up to M be real Hilbert spaces, and Cj, J runs 1 up to M be closed and convex subsets of Hj, actually non-empty. And let beta Bj from Hj to Hj plus 1. J runs 1 up to M minus 1. Since we started from Hj, be boundary linear operator such that S, which is given in this form, which is non-empty, then the general split physics problem is to find a point X star in this S. That is, X star is in C1, B1 X star is in C2, then up to Bm1, M minus 1, Bm minus 2, Bm minus 3, Bm minus 4, up to Bm1 X star belongs to this LCM. So this is just like composition. So I think just find a point in this S where S is non-empty, and they proved strong convergence theorem for the modification of this CQ method, which solves this problem. Actually, this problem was introduced by Reh and Tayun in 2020, I think 2020. Yes, it's very recent. And another generalization of this split physics problem is the so-called split physics problem with multiple output sets. And this is also introduced in, I think this one is also in 2020. And it is given by 18. Let H and Hj, see the differences. H and Hj, J runs 1 up to M be real Hilbert spaces, and let Tj from H to each Hj be boundary linear operators. Then the split physics problem with multiple output sets is to find a point X star in gamma, where gamma is the intersection of C and the intersection of the pre-images of Qj's. J runs 1 up to M, and which is non-empty, where C is a non-empty closed convex subset of H, and each Qj is non-empty closed convex subsets of each Hj. J runs 1 up to M respectively. Therefore, this one is also one of the recent generalization of the split physics problem, and this problem was also introduced by Reh. So in this work, motivated by the previous works, we want to consider another problem, which is called multiple sets split feasibility problem with multiple output sets. So it is given here. We study this problem. Let H and HJ, J runs 1 RPM, very neighbor spaces, and let HJ, J run HJ from H to HJ be boundary operators. Then the multiple sets split feasibility problem with multiple output sets is to find a point X star in omega, where omega is the intersection of CIs and the intersection of the pre-images of QJs, where I runs 1 up to n and J runs from 1 up to m. And this omega is assumed to be non-empty, where CI are the non-empty closed convex subsets of H, and QJs are the non-empty closed convex subsets of HJ. So this is somewhat a generalization of the previous three generalizations: the multiple set feasibility problem, the multiple set feasibility problem with multiple output sets, and the generalized split feasibility problem. So this problem generalizes the previous three problems. So so in this case, the solutions of 19 fulfill that or satisfy that X star should be in each CI, and TJ X star should be in each QJ, and we can consider that when this n is exactly 1, so we have this 19 reduced to 18. 18 is the split feasibility problem with multiple output sets. So when n is 1, so this problem goes to this one. You see here, we have only this C, where C is the non-empirical convex subsets of this H. So in the proposed problem, it is in the case when we have a finite number of closed convex subsets of the first space H. So if n and the m are exactly 1, then this 19 also reduces to the classical one, the split feasibility problem. And here, our aim is to establish a simple, strong convergence and self-adaptive step-size method for solving this new problem in the infinite dimensional Hilbert space. So here, I'm going to give some basic definitions and the tools. So let H1 and H2 be Hilbert spaces with the inner product and the induced inner group. I stand for the identity operator on H1 and H2, and these symbols denote for the weak and strong convergence respectively, and we denote the fixed point of an operator T from H to H if it has, which is defined in this form. And I think everyone is familiar with these definitions, so I can skip them. And the metric projection can satisfy these basic properties. So the fixed point of the fixed point set of the metric projection on C is C itself, and this metric projection also satisfy these other four properties. These are the definition of like convex functions, strong convex functions, subdifferential, and these some lower semi-continuous and weakly lower semi-continuous functions. So these are just the lemmas that we apply to our convergence analysis. So I can skip this, and this is the lemma that we have used to prove our main theorem, as the previous presenter mentioned that. So here I'm going to present the main result of this work. So we consider here a multiple set split feasibility problem with multiple output sets with the set Ci and Qj, which are represented in this form. where Ci given in this form and Qj given in this form, where Ci is from H to this set and Qj is given from Hj to this set, and they are of lambda I and omega j strongly convex functions respectively. So here we consider that Ci and Qj are a level set of strongly convex functions. Moreover, we assume that all Ci and Qj are self-differentiable on H and Hj respectively. And for any x in H, and for each I belongs to this set, a subgradient Zi belongs to self-differential can be calculated. Similarly, for the second set, for each for any y in J, I mean Hj, and for each J belongs to this set, a subgradient can be easily calculated, and all operators of the self-differentials are bounded on bounded sets. And from assumption to L3, Ci and Qj are lower semi-continuous and weakly lower semi-continuous and convex functions. So here we defined some support sets of the involved sets Ci and Qj, which are defined here. C star IN is given in 22. So we can see here, this is the self-differential. I mean, self-differential. And so from 22, we can consider that if lambda I is 0, then definitely we'll have this term goes to 0. So when this 22 can reduce to 23. So this is just the what you call the half space. But if lambda I, each lambda I is greater than 0, then for each I, this C star can be defined in this form, just by after passing through some easy steps, we can rewrite C star. We can rewrite 22 into this form. So we can also easily show that this is positive. This one is greater than 0. So we can see that this set is a ball which is centered at this point, having radius r which is equal to this one. So similarly, we can C star is also non-empty because C star is a support set of this Ci, where Ci is non-empty. So they are non-empty all. Similarly, we can define this support set Q star Jn, which is given in this form. So similarly, if omega j, if this is 0, then this goes to 0. So this one can reduce to this half space. And by a simple calculation, we can easily show that this 24 can be rewritten in this form. So we can also show that this one is positive. So Q star is a ball which is centered at this point, having radius r which is equal to this one. So C star IN and Q star JN are nothing but they are closed balls with their own radius and centers. Similarly, Q star is non-empty because it is the support set of Qj, where each Qj are non-empty. So this is the proposed algorithm. We named this algorithm as an outer quadratic approximation algorithm. So we choose two real spaces alpha n and rho n belongs to 0 and 0 2 respectively. We satisfy these two assumptions. And again, we choose an arbitrarily initial point x0 in H, and we set n is equal to 0, and we choose the weights delta ni and the parameters beta j, which are all positive, and the summation of beta j's are 1, and the summations of this delta nij, I mean ni are 1, which satisfy this properties. So the iterate method is given here. Given the current iterate xn from belongs to H, we compute the next iterate xn plus 1, which is given by this one. So this is the convex combination of the projections onto the ball C star in of this this term, where this tau n is the state size, and these are the balls given in 22 and 24, and the step size is defined in this form. Tau n is defined by this one, rho n times the summation of beta j of the norm of this term square, where theta n is the maximum of 1. Actually, you can choose any positive number, so it is the maximum of 1 and this term. So if xn plus 1 equals to n, then we stop. Otherwise, we set n equals to n plus 1 and we go back to step 1. So if lambda I and omega j are 0, then all the functions ci and qj are just convex. So we can have an algorithm that that can solve the problem which is different from this algorithm one. So we have the first result, the lemma 9. Assume that assumption 1 up to 4 hold, and let xn be any space generated by algorithm 1, then this one is 0. If on then if this is also 0. So actually it seems they are similar, but they are different. You can see here we have the adjoint operator, the adjoint of the operator. And the second dilemma is assume that the solution set is non-empty, and let rho n and alpha n be the spaces defined in algorithm 1. Let xn be any space generated by algorithm 1. Then for all x star in the solution set and n an element of or belongs to capital N, it holds this inequality where hn is given by this one, and the space xn is bounded, and we have for all x star this inequality also holds. So as you remember, the lemma I mentioned at the end of the preliminaries, we are trying to just relate this inequality with that lemma. So we apply that lemma in the convergence analysis. So this is the main result, theorem 11. Assume that the solution set of the multiple set splits reducibility problem with multiple outputs in non-empty, and the spaces rho n and the alpha n satisfy assumptions A1 and A2 in algorithm 1. Then any space xn generated by algorithm 1 converges strongly to the point x star, which is the projection of this point to the omega. So by setting n and the m exactly 1, so this problem 9 can reduces to problem 4, and we obtain the following result as direct consequence. So this is also a new method that solves the classical split reducibility problem, where the step size is given in this form, and these are the balls where n and m are exactly 1. So any space which is generated by 26 converge strongly to this point of the split reducibility problem. And for n is equals to 1, similarly, for n is equals to 1, the problem reduces to problem 17, to the general split reducibility problem. So again, we will have another new result that solves problem 19, which is given in this form. You can see here. Here we don't have the summations, the convex combinations of the project. We have only one n. So this is the only difference, where these are also closed balls, and this is the step size where theta n is given here, maximum of 1 and this time. So under these assumptions, the sequence xn generated by this 27 strongly convex to the projection of the point 0 to the solution set. This is also another new result. So when m is 1, we have this, the multiple sets split feasibility problem with multiple outsets reduces to this problem. So here we define that H1 and H2 be two reliable spaces, and T is from H1 to H2 be boundary operator with its adjoint star. Find an element X star such that X star is in E, where E is given in this form. So you can see here easily this problem is definitely different from the multiple set split feasibility problem. The difference is in this case. So we have only one set here. Therefore, this is also a new result which solves this problem. This result. Assume E is non-empty, then take weights delta Ni, which are positive numbers. Then for any starting point x naught and xn, the sequence generated by this iteration method, where the step size is given by this formula, can strongly converges to the projection of 0 onto E. So next, I will present one numerical example just to see the performance of our algorithm without comparing with any other algorithm, because as I tried to mention, this we reformulate the problem by ourselves. So this is the first algorithm for this problem. So we don't have to compare with any algorithm, but we can compare with the particular cases. For example, when we let n to be 1, so we will have an algorithm that solves the split feasibility problem with multiple outsets, and there are a number of methods that solves that problem. So we can compare with this our proposed method for fairness. And another reason why we didn't compare even with the particular cases is we consider these spaces. For example, we take H R4, H1 R3, H2 R6, H3 R9, and H4 H5, and we consider these sets. So in the first 3 problems, the particular case, the algorithms that introduced to solve those problems were methods that involves the projections onto the involved sets, except our methods. We introduced some methods to solve these problems, but they used to compute the state size self-adaptively, and we use the half space relaxation or the closed ball relaxation, something like that. So we are not interested to compare with our algorithms, but with the others, we realized that all the methods, it's like about 8 or 9 algorithms. All algorithms used the projections onto the involved status. But we know that there is no any unique formula to complete this projection onto the involved status. So we take this example technically. So we define this set as C1 up to C4 and Q1 up to Q5. These are ellipsoids. You know that there is no closed form to project onto the ellipsoids. So in our case, using 22 and 24, formula 22 and 24, we can define the support sets of each C and each QJ. So that means we can formulate the closed balls of these ellipsoids. So we will have a unique formula to project onto the closed balls. So it will be very easy. So we define this status in this form where these ZIs and WJs are the centers, and these are the radiuses, and these DIs and PJs are positive definite matrices, and we have the operators T1 up to T5, which are bounded and linear. So our aim is just to find a point in omega. So we know that an ellipsoid is a closed and convex set that can be represented as a sublevel set of a particular convex function. We can see in this reference 14. So indeed, we define CI in this form. Yes, this is from this one. It's nothing but from this one. We define, for example, C1. C1 from here, C1 which is equal to 1 over 2 or half of this star minus this R, 1. Similarly, Q5 is half of this star minus rho 5. So we define these functions. And we can consider that capital CI, which is written in this form, is just a level set of this small CI. And it can be easily computed that the gradient is given in this form. The gradient of this function is just this one. Similarly, the derivative of Tj with respect to Tj x star, we can find the derivative of the second function, and it can be easily seen that this gradient is norm of Di Lipschitz continuous mapping, and according to formula 22 and 24, we can form these balls of the involved status Ci and the Kj respectively, and the metric projection onto these balls have their own closed forms. So our method is very easy. So we choose these pointers and parameter values, and we use the stopping criteria to define this function for small enough equivalent. Then we found these results. So this is just the tolerance, and this is the initial point. So this is numerical results for our algorithm with different cases of initial points and the tolerance. Maybe here, since we have randomly selected values, especially for the operators for T1 up to T5, maybe the value, the numerical results, even in addition that the initial points are different. So somewhere, I don't know where, the time for, I think here is very bigger than of the other one, but I don't know which one. So you can see here also graphically for this initial point, we have for different tolerance, we have these graphs. Then this is the number of iteration versus the error for experimental results of our algorithm. So for the next, we are working with a more generalized problem of problem 19, and we are intend to give examples in infinite dimensional Hilbert spaces and more applications, just in different work, not this one. This one is already submitted. But for my friends or colleagues, maybe I can, this is also some of the references, but I can recommend that maybe someone also can do okay, for example, here we can see that these CIs are the finite number of non-empty closed convex subsets of this A, and Qj are the non-empty closed convex subsets of Hj. That means Q1 for H1, Q2 for H2. So anyone can generalize also this, where, for example, H1 have finite number of non-empty closed convex subsets. H2 has finite number of non-empty closed convex subsets. Just for each Hj, what if it has finite number of closed convex subsets? Not only one, but here there are only one. For each J, only one Q. So what is this? So this, anyone can take this as an open problem. So maybe in the algorithm,
Which means that for each Hilbert space, you take number of subsets, then you take the intersection of all those subsets.
Yes.
Still you get one set.
no. Look, what I did is, look here.
I understand you take one set from each Hilbert space, right?
Yes. So what if, for example, H1 has finite number of subsets?
But you take that again, you take the intersection of all of them, right?
That is up to you.
No, you know intersection. So you
You can take
define
the
that.
intersection or another method. You can use different methods.
Can you define that problem?
Yeah, actually in different form I'm working on it, but in the idea now, yeah, for example, you can introduce
You
something
take
here.
the intersection of all
For example,
let stores.
yeah, for example, you can use different notation here. For example, you can put J here, but here another
QI, yeah.
that one. So in the algorithm, you can use summation or another technique like selecting the maximum or the minimum, something like that. But in the problem, for example, for instance, you can take here Qj K, for example.
Yeah.
K runs from J to something or like that. So each J, I mean each Hj can have finite number of non-empty closed convex subsets. So, for example, if I want to modify my algorithm, for example, here, if I want to modify it, I will have like here, I can have here inside of here summation.
Yeah, number of projections.
Yeah.
I understand.
Summation, or you can choose another.
So you are working on,
Yeah,
you are working on.
not this one. I'm working on another one. This one somebody can go for it.
There is a picture on the first tool where you can find the inverse of you. You understand? There is
Yeah.
a picture graph. There is a diagram. Second or third slide.
But the first problem is yes, I have. But
The first two
maybe can I finish it first?
already. Well, not finished. I just want to go.
Okay, this one.
No, I think second, there is a picture where you define the.
This one. Look.
No, please. Yeah, this one. how you can say this? What is the relationship that A inverse to intersect with C?
You see, look here. This is three image of C. You see? This is C, which is surface of H1.
So you
So
are
this-
already
this
saying
region
that
is
C and Q have intersected.
Yeah, because we are seeing that they intersect in that.
Okay.
We are
A
seeing-
inverse.
Yeah, we are, yes. Yeah,
That's-
but mathematically, you can see that this is convex and colored because of the behavior of this and Q and this is bounded now. But for the non-infiniteness, we are seeing. Okay, thank you. This is all.
Thank you very much for this wonderful talk.
This,
Ah.
Huh?
You can do the same thing. Yeah, the question how we know that this is non-empty? Well, how we know that they have some common
We are
element?
seeing this.
You are assuming this
Yes.
that A inverse of Q.
Yes, we are seeing it to be like this one. Like we are saying that this is non-entity. You see this region? This is our assumption.
So it may possible that A inverse, outside of C, may possible that. But you assume
Not,
that.
yes, it can be outside of C, for example, this part, but we are seeing that
Yeah,
the intersection is non-entity. For example, this part is outside, you see? This is outside, but this is inside, so this is the intersection. So we are seeing to have like this. Another.
There is more questions? Any more questions?
Thank you very much. This is very nice. Very good. So, mine is, can you go back to like
22.
So your function there is defined from this to this.
Yes. Extended in numbers.
Go to this. Good. So this is I and student and Q state. Okay, this lambda I am complementary. You say they are only complementary.
Yes. Huh?
No,
No, CI and
no, lambda
QJ.
I and omega bar Q are only complementary.
no, the
Yeah,
function
that's
is
like-
not the constant, no, the function is CI is lambda I strongly convex function.
Okay.
And QJ is omega J strongly convex function.
So this something convex about verifying CI and QC.
Yes, yes,
Rather than lambda I.
yes.
I think it's kind of made.
Yeah, maybe the which are
Yes, yes. So I don't know, do you how like, do you see any work, or can you consider relaxing this complex? Like instead of taking something complex, take normal complex.
yes, yes. Normal convex means half space. We are using the half space relation. That means
So if you take something complex.
yeah, we have been working on this.
What about
That means when you use that one, the supersets of the CI and the QJ, they will be half space. This half space, they are linear forms. So That's why we say the outer linear approximation method. But if they are strong, if the functions are strongly convex function, so we will have quadratic term.
Yeah.
We will have an outer quadratic approximation method. The name stems from this one.
And quadratic.
Yeah, you see. No, this term, yes. You may have different types of format, but so this is the board.
Yeah.
But if this lambda I is 0, this term will be 0. So this one can reduce to this. This is linear upstairs.
Yes.
So we will have an outer linear approximation method or upstairs relation.
What about the previous lines?
Such 7, 7. These are standard assumptions.
I think we are right.
Yes. These are standard assumptions actually.
Okay. Thank you very much.
Thank you very much, Dr. Bush. I actually have some questions for you. Can you go to slide 14? That's the main algorithm.
1 4
Yes.
1 4 0.
1 4.
This is 1 4.
Oh, okay. I'm concerned about this equation 16, which is the main problem here, as multiple set split feasibility problem.
Yes.
Okay. What is the difference between multiple set split problem and just split feasibility problem?
Yes, please.
Yes.
The only difference is on the number of
Sets.
closed subsets.
Yes. So from this 16, one can see that here we have intersection of finite set CIs, right? We also have intersection of QJs.
So we have,
Yeah.
we have only one C, only one Q. That means it reduces to, it can be written in the form of the split one.
Okay. Okay, but all the generalization are built in this sense.
Yes.
So my concern here is we know that. Okay. We are going to that also. My concern here is when we take intersection of closed and convex sets, you have a closed and convex set. So what is the difference? What actually is the real difference between this one and the one with just one set? Because if you say when you reduce T to be 1, you have the other one. And as well, when one consider one set, you can call it just the intersection of this finite. I mean, like, okay, I can consider this problem as just split feasibility problem. Calling my C as just the intersection and my D as the intersection of QJ.
Yes, you can call
So, so generally now, calling this multiple set split feasibility problem as generalization of split feasibility problem, to me, I could not see that, because from all the problems you can relate, from feasibility, split feasibility problem, you can come back to this one because they are under the same assumption. The closed and convex set holds, even when you have finite number of them.
Yes.
That is actually one thing I have been wondering about, because this is very interesting area and I have seen it has a lot of application. Yeah, I don't know if it has some certain advantage over the one with just single set.
Actually, for example, as we say, you can write this as a just a problem.
Yes.
But when you write in that form, you will say here X star is an element of C where C is the intersection of CI, right?
Okay, yes.
Such that its image is also in Q, where Q is the intersection of QJ.
Yes, I can consider that. Yes,
But this C and the intersection of CI,
that's no problem.
yeah, but in how many states you are looking the solution? It's not exactly.
Oh, our target, we are looking for just X, right?
Yes, X.
X.
Theoretical one is only in one case, in C. But in this case, it is in Q1 and Q2 is all C.
Yes.
Or
Even with that, I don't know if you understand my argument. Now, if I call intersection of CI as just C, I'm also looking at X inside C, which is the same as looking at X inside intersection of CI.
I think one
That is the difference I want to see. What is the difference? Okay.
all this.
yeah, it is
And then
Now look at the problem for 16. We are looking at X from intersection, not X from CI. There is two different things. When you say X from X1, for example, from C1, X2 from C2, is different from X from intersection. I think that's to understand.
in the intersection, it should be an element of each set.
Yes. Yes.
The classical problem is only in one thing.
Oh.
Understand?
This is particular problem. If they want to visit that
I understand you. Okay, now let me come again to my question. Maybe then you will understand. Now, suppose I assume that this is a general problem, the split feasibility problem. Let's assume it is general. That is to say, if I consider T to be 1, for example, R to be 1, we have back split feasibility problem. Okay. Somebody now that study only split feasibility problem, he can also take his set as one set, referring it to be just the intersection of CI. You understand? And he can also refer the intersection of QI as one set. Now, if you look at that point from C such that TX star is also in his Q, will it be different from this one?
Let me explain the point.
Okay.
For example, letting the T and the R are exactly 1, and letting the C becomes the intersection of QI and Q becomes the intersection of QI. This is okay.
In my opinion, are the same.
Because when you let T and R exactly 1, 1.
I think we may continue this one after. But I have other questions. Let me just proceed to other questions.
What do we need for it? What is C?
Yes.
You only need C to be closed, correct, and non-empty.
Yes.
So now, what sign is saying? I can decide after taking the intersection, I call it C.
You have only one.
Yeah.
That is after you work a lot, you will have only one set, which is the intersection.
Yes.
You understand? But what is the technical problem? Is that one with only one set? The image and the
Maybe after, please. Yeah. My question again is on the main algorithm. Why did you call it outer quadratic approximation?
Yeah, because the relaxation is of the quadratic exponent. In the expression.
Can you show, please? Because I want to understand why is it called outer quadratic? Because this is the first time I have seen this word. Yes.
Okay. You see this
Okay.
expression? This is half space. This is the board. This is just quadratic. This is just
Okay.
linear.
Okay.
Then it came from these expressions. If I am going to relax the algorithm onto the half spaces, just I can name it as an outer linear approximation. Because why I say outer is these sets are the supposed the involved. Why I say linear or linear expression. These are quadratic. Just came from this.
Okay. Please, if you have questions, ask. Any question, please? Time is again. Any question from online? Okay, thank you very much. I think it's time we move to the next speaker.
Okay, thank you so much.
Please, let's clap for Dr. Hui. I think the next speaker is going to be presenting from online.
Yes.
Oh, thank you very
Good
much
afternoon.
for being with us. Yeah, good afternoon. So the floor is yours now. Can you start by sharing your slide and then move on?
Now you see my slide.
Yes, we can see.
Everyone can see.
I think it's clear to everyone.
Okay. You hear me? Is the sound is okay?
Yes.
Okay, thank you. Let's start. Can I start? So, good afternoon, everyone. I am Pontip Promsinchai. Today, I would like to present my results on the block coordinate descent method for Cartesian variational inequality problem. So, first, I would like to recall the variational inequality problem, and then we will move to the our main problem, Cartesian variational inequality problem. And the next one, I will propose the algorithm so-called the cyclic block coordinate type algorithm for the Cartesian variational inequality problem. And the last one is future work. So let's we recall the variational inequality problem. Let X be a non-empty closed and convex subset of a real Hilbert space H, and let F be an operator from X into H. So the variational inequality problem, or for short VIP, is the problem to find a vector X star in the set X such that the inequality 1.1 whole, that is the inner product of f x star and x minus x star greater than or equal to 0 for all x in the set X. So it is well known that the variational inequality problem are the powerful mathematical tool that can serve as a unifying framework for capturing a wide range of the application arising in operation research, finance, economics, and so on. So next we move to the Cartesian variational inequality problem. So first, I would like to recall the some notation will be used in this talk. For I equal to 1, 2 to m, we let H1 until Hm be a real Hilbert space with an inner product respect to I. I is the from Hi. The Hilbert space Hi, we have inner product respect to H. For the Hilbert space H1, we have the inner product H1 respect to H1. The Hilbert space H2, we have the inner product respect to H2. And it's in the norm, we denoted like this. And now we let H I would call this this notation the big H be a product space of the Hi for all I equal 1 until m. Then the big H divided by 2.1. So we define the inner product for the big H by this notation is the summation of each I. If now we have vector u and v in the big H, then the inner product is the summation of ui, vi respect to I for all I equal 1 until m, where ui is the I component in the vector u, and we also then we see that the inner product space become of H. This space is the real Hilbert space, and we denote the norm by this one. So for more understanding, now if we have H1, Hi is R2 for all I equal 1 until 5. Now we have 5 H, and then the big H is the product of R2 5 times, then the big H is R10. Then now if we have the vector u and v in R10, u is u1, u2 until u10, and v is v1 until v10 like this. Then the u of 1, this notation is like the sub vector is the block 1 in R2 is u1, u2. If for u of 2 is a u3 and u4 like this, until u5 is u9, u10, and for the v also, or u is the vector in H is R2. So the inner product defined by this one is the summation of ui, vi respect to I for all I equal 1. Now for in this case, m is 5 like this. So next, I would like to introduce the Cartesian variational inequality problem, or for short CVIP. The Cartesian variational inequality problem is the problem of the form of variational inequality problem, where the set X defined by the product of Xi, and I would like to say this set is a big X like this. So that means in this work we consider this problem where X, the big X, is the product of Xi, where Xi be a subset of a real Hilbert space Hi. Then the Cartesian variational inequality problem is the problem to find a vector X star in set X such that the inequality 2.3 whole is the inner product of Fx star and X minus X star greater than or equal to 0 for all X in the big set X. And the operator Fx defined by F1x. F1x is the one component of the vector Fx. Okay. What is the difference for the variational inequality problem and Cartesian variational inequality problem for the compute of the inner product? So if now we let x is R4 and operator f is R4 to R4, if we suppose that now the vector x is 1, 2, 3, and 4 like this, and x star is the vector 1, f x star is the vector 1. Then we compute the inner product is a normal. It's just combine multiply point by point and then combine it together, and then we have the inner product is 6. And then for the Cartesian variational inequality problem, now in the same case, now x is R4 and each xi is R2. So if we let the vector x is 1, 2, 3, 4, then the x of 1 is the vector of 1, 2, and x2 is 3, 4, and x star is the same like this. So when we compute the inner product is the summation of the inner product in the Hilbert space H1. Now H1 is R2. This also respect to R2. So then we obtain same. So from here, from this example of the computation, so you see that the Cartesian variational inequality problem is effective when the dimension of the problem that we considered is very large. We just this one from the previous one, we have to compute the dimension is 4 and now just 2 like this. So this is the motivation for us to consider the Cartesian variational inequality problem. So for the motivation in the for the other problem, for the high dimensional convex optimization problem on the large scale convex optimization problem is to minimize fx subject to x belong to the big set big X, while this one is the product of xi, and the vector xi defined by this one, and each xi belong to a set xi be a subset of Rni, where the summation of ni I equal 1 until m equal to the dimension n. So in this case, we the dimension n is possibly very large. So it is well known that the optimality condition of the problem 2.4 can be represented as the Cartesian variational inequality problem, where the operator fix is the gradient of fx respect to xi. Then that means we solve the problem, the Cartesian variational inequality problem 2.5. So for the next motivation is from non-cooperativeness game. So this problem we consider a classical non-cooperativeness game among D player, where the I player is associated with the statistic xi, where xi belong to the set xi be a subset of Hilbert space xi, and we let fi of xi and x minus I denote the cost function of the I player, where this notation x minus I denote the collection of the action of the other player. So the goal of each player is to minimize the value of the cost function for any arbitrary strategy of the other player. By solving this problem, minimize fi of xi respect to x minus I, where each xi belong to the set xi. So a Nash equilibrium is the x star defined by this one, where the no player can obtain by lower cost by dividing from his strategy if the strategy of the other player remain unchanged. So it is well known that when for all I, the set xi is closed and convex, and the function f is the differentiable convex function with respect to each xi, then the resulting equilibrium condition of the Nash game are completely captured by the Cartesian variational inequality problem, where f the operator fix is the gradient of fi respect to xi. That means we solve the Cartesian variational inequality 2.7, where the fi defined by this one. So from two example of the motivation, we our motivation is like the two way. The first way is we have the big thing, and then the big thing like the high dimensional optimization. Then we can separate it into the small one, and then we can apply our integrated problem, Cartesian variational inequality problem, to solve this kind of problem. And for another type, if we starting from the small one xi, and then we can combine it together, and then we can apply the Cartesian variational inequality problem to solve it also. So now we move to the our proposed cyclic block coordinate type algorithm for solve the Cartesian variational inequality problem. First, I would like to recall some useful tool and some property for which will be used in this work. For the operator f, we will call f is monotone if this inequality holds, and we will call the operator f is eta strongly monotone if there exists the constant eta greater than 0, such that this inequality holds. And we will call the operator f is L Lipschitz continuous if there exists L greater than 0, such that this inequality holds. And we will record the metric projection of the vector x onto the closed convex subset x of Hilbert space H. We denoted by P of x on the set x is the arc minimum of the norm of x minus y and y in the set x. So now I would like to recall some algorithm for solving the variational inequality problem. One of the classical method is the so-called projection gradient method 3.1. So in order to guarantee the convergence of this algorithm, this method requires the assumption on the operator f is strongly monotone or inversely monotone. So for the next one, our well-known projection type method for solving the variational inequality problem is the exact gradient.
Please,
method.
hello? Please,
Yes?
your internet is not good. I don't know. We can't hear you well.
Oh, sorry.
Maybe you can
Maybe it's
reconnect.
for me.
I think so.
How to fix this? And now you hear me? Sorry.
Even now, it's still breaking.
So now it's good or not?
It's still not good, please.
Oh, sorry. Oh. Please wait a minute. I will change the internet.
Oh, I think now it's okay.
Okay.
Yes.
Okay, can I continue?
Can you just make use of the audio? Maybe I think if you stop the video, maybe that way it will work.
If it's not full screen, it's okay. Now it's okay.
Continue.
It's almost finished. Okay,
It's still not okay.
that's okay. Sunny, please. It's okay or not? If no, I will change the internet.
Yes, it's
The
okay. You
sound
can
is still
continue.
not clear.
Okay. Okay. So next, now it's the exact gradient method. So to is what proof that if the solution set of the VAP is not empty, then and the operator F is monotone and Lipschitz continuous, then the sequence generated by the extra gradient method can convert really to the solution set element in the solution set of the VAP. So for next, the inspired by the extra gradient method. Sensor modify the extra gradient method by replacing the second position onto the closed and convex subset X with the half space Tx like this. And then they call this method subgradient extra gradient method. And they show that if the solution set of the variational inequality problem is not empty and the operator F is monotone and Lipschitz continuous, then the sequence generated by the subgradient extra gradient method convert really to the element in the solution set of VAP. So for recently, there is some algorithm to solve the VAP, so-called Haupen type subgradient extra gradient method by using the idea of the Haupen method for the fixed point problem and the subgradient extra gradient method in 3.4 like this. Then they show that if the solution set of VAP is not empty and the operator F is monotone and Lipschitz continuous, then the sequence generated by the Haupen type subgradient extra gradient method converts only to the element in the solution set of VAP. So from the another motivation from the high dimensional convex optimization problem, so-called cyclic block coordinate gradient projection method. When given x0 in Rn and alpha greater than 0, then for the iteration k is 0, 1, and so on, we set xk0 is xk and compute for I equal 1 until m by xik of j. If j equal to I, then we update that block by the projection onto the set xi of this vector. And if not, if j not equal to I, then we fix that block with the same period 1 is xk I minus 1 of j. Then we do like this until I equal to m, and then update xk plus 1 is xkm. So now this is our proposed algorithm, cyclic block coordinate projection algorithm, and for short CBCP, for solving the Cartesian variational inequality problem. We starting from x0 in the H hyperspace H and parameter alpha greater than 0 and the sequence beta k in this interval. So for each iteration, k equal to 0, 1, and so on. 7, we set xk 0 is xk, and we compute yk as for I equal 1 until m, we compute yik of j is if j equal to I, then we update that box, and if not, we fix is the same as previous one, and then we obtain yk is ykm. Then we update xk plus 1 by using the idea of Halpern method. Beta k x0 plus 1 minus beta k yk, like this. That means for k, if now for iteration k is 0, we would like to we have now we start from the x0, and we would like to compute the x1. Now we set x0, 0 is the initial point x0, and now for I equal to 1, we update only the block 1, by projection onto the set x1, and then we obtain y0, 1. Then for next, for I equal to, we update only the block 2 position onto the set x2, and then we obtain y0, 2. We continue for all block until I equal to m, and then we obtain y0m. We set y0m is y0, and then we obtain x1 is beta 0 x0 plus 1 minus beta 0 y0, like this. So now we have the convergent results for our proposed algorithm. Let K be a sequence generated by our proposed algorithm, cyclic block coordinate projection type algorithm, and we assume that the solution set of the Cartesian variational inequality problem is non-empty, and the operator F is Ita-Songli monotone, and Fi is block Lipschitz continuous, and the sequence beta K and alpha K satisfy two conditions. Then we obtain that the sequence xk generated by our proposed algorithm convert solely to the unique solution of the Cartesian variational inequality problem. So for the next work, I try to apply our proposed algorithm for some application. For example, non-cooperative multi-agent network, competitive power market, some machine learning, that's like the big data, something like this. If you have some suggestion, please. So, and next, I would like to try, I will try to use the Arthur selection rule, for example, as random rule or the parallel algorithm also. And I try to improve the algorithm for the Cartesian variational inequality problem as in the development of the algorithm for the variational inequality problem. So on. Thank you very much. If you have question or suggestion, please.
Thank you very much for this wonderful presentation. Please, anybody with question? Any question?
Yeah.
Okay, please, I have a few questions for you.
Okay.
The first one is on the motivation. You made mention that from the first motivation, you explained to us how the difference comes about. That's the difference between classical variation inequality problem and then the Cartesian variation problem. Can you go back to that slide, please?
This slide on the
example you gave.
example.
Yes. Okay. So for this Cartesian, you ended up having the variation inequality problem here to give you 6 as a number.
Mhm.
So what exactly is the motivation? I want to understand that, please.
I see. As a for the variational inequality problem, if we have the vector in the whole space dimension now is R4, then we compute the inner product. We have to take the inner product of whole vector, and for here for the Cartesian, we have we take the inner product on the subspace or like the subvector on each xi. You think if now we have the high dimensional, for example, 10 million, something like this. I'm not sure it's a big or not. If we compute at each iteration, we compute the biggest one, then you have so much time to compute at each iteration, and now you just compute just the small one. So this is the motivation to compute for the Cartesian variational inequality problem.
Okay, Dr. Abakar, please ask your question.
My question is, can I see your proposed algorithm for this kind of variational inequality?
You mean this one? My propose.
Is it subgradient or extra gradient type method you use?
Now, for me, for my algorithm, now I use the gradient, and the next step I will use the extra gradient.
Extra gradient?
For now, for this work, I use the just only gradient. You see, this one is just like the gradient projection. If this one is like this.
Oh, I see. Okay, thank you.
Yes.
Please, one more question on this.
Yes.
Why did you call it cyclic block?
Because now if the cyclic is formed, we only compute the block that j equal to 1. Please see this one. If now j is 1 and I is 1, we compute only this block, the first block, for block 1. And for the next I equal to 2, we compute only the second block. Is the cyclic 1, 2, 3, and so on. Or you can use the rule for the cyclic rule, like the modulo, something like this. Is okay, fine.
Okay, thank you very much. Any questions? I think that is all from the on-site. If there is any question from online participant, can you ask? Oh, no question. That's all.
Okay.
Thank you very much for this presentation.
Thank you very much.
Yeah.
Okay, thank you all for participating on this seminar. And we are really much grateful. See you next time. Okay.